D to Q to alpha beta transformation, where all these DC components will be converted again back to AC components. Then you can feed any modulation methods, which going to control all the 6 devices of your inverter. It can be a space vector modulation or a standard modulations of sinusoidal pulses modulations. Then you can easily control your inverter. This is a standard algorithm. What I discussed here, I showed you here the same block. Now slightly we are adjusting for a field weakening region, where we are going to calculate from the point of voltage. So when you are taking these two values, this is going to control your flux, this is going to control your torque, and we are going to find an absolute value. It's nothing but we are going to calculate only the amplitude. So root of x square plus y square. And this parameter is going to be the feedback value of your stator parameter in terms of voltage. And this is the maximum value of your stator voltage, which is control the flux. So this will be compared, and the error is going to the PA regulator. So as you know, this PA regulator will try to trap the reference value which is fed to the system. And from this, we are going to calculate what is omega R. So in the previous case, we have fed omega R directly. Calculated, we are feeding to the system. Whereas in this case, omega R is calculated from the loop. So from the loop, we are calculating omega R with the reference value. So in this way, we avoided the flux weakening region. Then this is compared with the actual value of your rotor flux, then PA regulator is regulating. Of course, we need to do also for the stator current saturation. So stator current saturation maximum value is taken and compared with the two feedback available here. So I have two values. I made ID because it's very important. ID is going to control the flux, which is the field parameter. It is given x square compared with the reference value, and this feedback error is fed to here to calculate your torque. So in this way, you reduce the field weakening effects in your electrical machines so that you can have more dynamic vector control. Thank you very much for attending this presentation on the control of AC machine. Now I like to present for AC machine, which is in another version. How to control synchronous machine, that is most important, because in synchronous machine the size is very small and it has more advantage to have a high speed when compared to induction motor, because when compared to the efficiency of your synchronous machine is very high when compared to induction motor, and you can have very finite speed control. And of course the major advantage is you can have reduced rotor losses. That is no much better than the induction motor. Of course, you can have a very reduced weight when compared to induction motor for the same power rating, reduced by a factor of 25%. Then, of course, you can have also the power rating can be reduced with around 25% in case of comparing with induction motor. So then, of course, you can have a very high torque, and the behavior will be very smooth. And of course, you can have the rated speed 1500 rpm means 1500 rpm. You can able to get it from AC machine from a permanent magnet synchronous machine. What are the disadvantage? The disadvantage includes very complicated to have a cooling system in your synchronous machine when compared to a induction motor. Of course, there is a difficulty to control in group, because if you go to cotton mill, many multiple induction motor are driven from a single inverter and able to control the propulsion of the threading. Whereas in case of synchronous machine, it's a complex process. The complex process is that we can't able to have a group drive system. Of course, if the inverter fails, then it's a tedious part. We have to isolate the motor and the inverter. Whereas in case of induction motor, we have other strategies we can able to control even under faulty conditions. How to control? Same logic. So the speed can be taken as a reference and can be compared with a sensor. Here we used another technique, sensors based control algorithm. So this is actual speed of your motor, and compared to the reference speed, we put a PA regulator. The purpose of the PA regulator is to control the speed of reference. Obviously, the input is going to be the voltage, so that you are getting a current reference, which is controlling your torque. And this is compared to the actual value of your current, which is calculated from the parameters of the current which supplies the motor. So then I can have a reference for your flux. The flux reference is compared to the actual value of your flux producing current from the machine. Then put a PA regulator for both the cases, so you can be able to generate the reference, which is in terms of voltage for your flux and torque. Then use clock transformation, inverse clock transformation, so that all these parameters of DC will be converted into AC. Then you can feed to your inverter to control 6 parameters of your devices to control the inverter. And in this case, last case, if you look at the difference, we used indirectly to calculate the angle theta. In this case, just integrate your speed, you can be able to calculate theta, and you can feed the blocks. And these are the performance we got from the numerical modeling. So this is going to be your flux producing component. Initially it is 0 until 20, then there is an increase in the speed. Why? What is the reason? Because the speed starts in this case is 0 until 20. After 20, the reference goes to the maximum value. You can see it's 1 because synchronous motor runs at rate speed. It's the maximum value, the transient, then reaches the smooth value of the flux requirement. Obviously, then during the steady state period, so this is an oscillation period. And this is speed response. So initially it is 20, until 20 it is 0, then start increases as the reference goes to the maximum value 1 and tracks the value and reaches the maximum speed of 1500 RPM or whatever be the machine parameter. Here it's shown in per unit value. And this is the torque producing component. So initially the machine is 0 speed until 20, and the speed starts at 20 seconds, so that it starts also along with the speed. Then once the speed reaches the steady state value after the transient, the no load current requirement for the torque is available. So the motor is not loaded here. And this is the angle theta. What happened when I integrate the speed? So you can have a look. 360 degree of rotation starts after 20 because the speed starts at 20 and it is propagating like 360 degree rotation. And these are the parameters of your flux and torque components in voltages. If you look at here, what are the parameters I can get? So how it looks. So these are the parameter for your torque producing components and flux producing components. And when the speed is reached the steady state value, they also reaches the requirements. And this is the modulation changes, how it looks. And initially the speed is 0. Then there is a transient. Once it reaches this around the time 60, rated speed. Similarly, you can have a behavior here. When after the 60, it reaches the maximum modulation. So maximum modulation is 1. The maximum it reaches around 1. So it's maybe 0.9 is required to drive the motor at 1500 RPM. And these are the performance which we got for flux producing current. So flux producing current is kept at the maximum value, and this is going to be the torque producing component. Flux producing current is kept at 0, and this is the torque producing components. And torque producing components are going to vary with respect to the time, because we are going to control, in this case, the motor at different conditions. For example, at time 0, the maximum speed, the reference is set. At time 400, it comes back to 0. Again, at time, say, 650, it goes to the maximum value. So all the cases, the speed follows the reference value after a transient period and a small peak overshoot. That's why if you look at the behavior of your torque also varies accordingly. So until 200, the rated speed is kept. So the torque is also at the max it goes. Then when it reaches the steady state value, it comes back to the no load torque requirement. Similarly, the reversal of the speed, all the cases. So it regulates according to the requirement of the speed. And this is the modulation index. Initially, you can have a look. It starts with 0.2, then goes to 0.4, then backs to minus 0.2. So it's a variation with respect to the requirement of the speed changes. And this parameter shows you in detail what is going inside your electrical machine. and the parameters are calculated. So this is the response. You can see we are talking how the transformation looks in AC